So today, lesson 24C, we shift our focus from matrices to vectors. We're going to take about 3 days to make it through the important parts of vectors. Today, day number 1 of arithmetic of vectors. And we're going to focus on performing addition with graphing, a graphing method, and then also algebraically as well. So, if we have a triangle like the one that is graphed up here, and I take and I move it that direction, and then I take that one and move it this direction, we can think of that as the original triangle translated. Arrows will be used to indicate the movement of one of the vertex points through each translation. So if I take that point and move it to there, and then take that point and move it to there, that is an example of how we can use rays, which we sometimes call vectors, to track that movement. And the two red vectors showed the first movement, then the second movement, whereas the purple one shows one movement to get from the original shape to the new shape, or a single translation, if you want to think of it that way. And as I just mentioned, these arrows are sometimes referred to as vectors. And so I know we've got a blank area to fill in there in our notes. All right, and so I'll call the first movement of that vertex to the translated vertex vector V, and I'll call the second one vector W, and I will call the one movement to get from the original to the new vector R. And those are already labeled for you in your notes. Now, before we move on here, I like to, if I see something in a movie, I like to that mentions something that we're talking about, I like to put it in the lesson. So the volume is a little bit low on this, so you'll have to listen carefully here.
Hey. I'm applying for a new film loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new weapon. Piranha gun! Oh yes! Fires like piranhas. Ever seen one before? Now you have my invention. You want a demonstration? Oh! Ow! It's so difficult sometimes to get the line back inside.
Mr. Perkins, you see now?
Okay, as he said in the short little video there, a vector is a quantity that has both magnitude and direction. And we've got blank areas to fill in here. So we're going to start today's discussion by talking about what we mean by direction and what we mean by magnitude. So first of all, the component form, which we will utilize a lot when we're dealing with vectors, the component form of a vector, this is an example of one, 5, -2. Notice that those are not parentheses. And the reason why is if we had parentheses, that would be denoting an ordered pair, whereas this is denoting a vector, or the component form of a vector. By magnitude, we are talking about the distance an object moves. Now, we have dealt with distance before, and we will bring that back in today. It's just that when we're dealing with with vectors, we refer to it as magnitude instead of distance. But that's what we're really meaning by this, the distance an object moves. And so when we see those double bars around a vector, that automatically means that we need to find the magnitude. So that is telling us to find the magnitude of vector V when we have those double bars around it. And we're continuing to fill in blank areas here. All right, moving on. By direction, we're talking about the direction in which the object is moved. And we started today's lesson by me showing you a translation of a triangle. And we could describe the direction that it actually moved, which we had done when we did translations originally. Arrows or directed line segments are one way of representing a vector. In other words, they kind of look like a ray. In later math courses, both magnitude and direction may represent differently. And I will come back to that a little bit later in the lesson. So let's go back to that original picture where we took a triangle and translated it and then translated it again. And it looked like this. And so in that previous example, two vectors, vectors v and w, were combined to form vector r. And this is what is referred to or meant as adding vectors. Adding vectors. And that is our main focus today, adding vectors. And so, vector r can be thought of as vector v plus vector w. And I believe that that is already in your notes. And when we find the sum of two or more vectors, that is called a resultant vector. So that purple vector there is called a resultant vector. And we'll keep referring to it as that as we go through the next couple of days. Okay, resultant vector, and that is the purple one. All right, so before we can actually get into adding vectors, we got to go back to magnitude and discuss how we find magnitude. And I told you that it's really since we're finding the distance, we've done that before. So if you want to find the magnitude of vector w, which is what that is telling us to do, we're essentially finding the distance from the starting point to the end point of vector w. And so 2, 3 was the original ordered pair that we moved. And if you go back to your original picture, you'll see that. And it ended at 10, 13. Now once again, if you look back at the picture, that's what you'll see. Vector v started at 2, 3, and it ended at 10, 13. So if you want to find the magnitude of vector v, you need to find the distance from 2, 13 to 10, 13. So remember, the distance formula is the square root of x sub 2 minus x sub 1, quantity squared, plus y sub 2 minus y sub 1, quantity squared. So everybody go ahead and do that. This is not the first time that we've used the distance formula, so go ahead and do that. All right, so let's take a look at this. So we could use the distance formula, and just a reminder, if you wanted to, you could also just use the Pythagorean theorem from the actual picture. And the reason why that's just as good in these types of situations is because of the fact that you will always have a picture, and so you could do it that way as well. But if you're going to use the distance formula, we end up with this, because x sub 2 is 10, and x sub 1 is 2, and y sub 2 is 13, and y sub 1 is 3. Do some simplifying, and we end up with the square root of 164. And as a simplified radical, that is 2 square roots of 41, because the square root of 4, or 4 is the largest perfect square that goes into 164 evenly. So we split that up into square root of 4 times square root of 41. The square root of 4 is 2. And then as a decimal, and once again, you can use a calculator on the decimal, square root of 164 to the nearest tenth is 12.8. All right, so the length or the magnitude of vector w is 12.8. Can I get all of you to go ahead and do number 2? And in number 2, you are finding the magnitude of vector w. Same idea. And vector w started at where vector v ended, so at 10, 13. And vector w ends at 17, 8. All right, so let's take a look at number 2. I'm going to use the distance formula. And I end up with the square root of 74. And by the way, the square root of 74, the largest perfect square that goes into 74 is 1. And the reason is because the prime factorization of 74 is 2 times 37, which are both prime numbers. So that is a simplified radical. And then to the nearest tenth, the magnitude of vector W is 8.6. Let's go to the next page in our notes. And now, find the magnitude of the resultant vector. Now that was vector R, but it was also the magnitude of vector V plus vector W. So go ahead and do number 3. Same idea. And remember, that resultant vector started at 2, 3, and it ended at 17, 8. And if you looked at the original picture, you would see that. Now, once again, in all of these magnitude problems, well, at least these anyway, you could use the Pythagorean theorem if you wanted to. But I'm going to stick with the distance formula. And so when we find the magnitude of the resultant vector, we end up with the square root of 250, which I know that can break up into square root of 25 times square root of 10. So that's 5 root 10 as a simplified radical. And then square root of 250 to the nearest tenth is 15.8. So the magnitude of the resultant vector is 15.8. So that's magnitude. And that should be pretty easy. Now, one quick note here, and add that to your notes. Note that the magnitude of vector V plus the magnitude of vector W is not equal to the magnitude of V plus W. Those are two totally different things. And to make sense of that, you could create a right triangle with a Pythagorean triple like a 3, 4, 5. That would be like saying 3 plus 4 is equal to 5. And it's not. It's not. Okay? 3 squared plus 4 squared is equal to 5 squared. So it's really kind of the same sort of thinking. All right. Now, direction. For now, the only way that we know how to describe direction is up movement, down movement, left movement, right movement, and sometimes that might be described as north, south, east, west. So if you looked at vector V went up 10 units and right 8 units. So we might describe that direction as north 10, east 8. If it was more of a real-world problem. Vector W from vector V is going south 5 and east 7 because it went down 5, right 7. And then the resultant vector, which started at the original point, and we're describing just one movement from the start to the end, that would have been north 5, east 15, because it went up 5 and right 15. So right now, that's kind of how we know how to describe movement, because we're talking about this in terms of translations. Hold on, let me back up a second, because I know some of you are still writing stuff down. All right, so that's magnitude and direction. Now, once again, as you advance through math courses, that will change slightly because we start involving angles and some other things. But for right now, that's how we're going to describe direction. All right, so now we've talked about arithmetic with regards to matrices, and we did that, and then we shifted to scalar multiplication, and then we shifted to matrix multiplication. And today we do the very beginnings of arithmetic of vectors, but that has a lot in common with matrices. So today and tomorrow we'll be dealing with adding and subtracting vectors. In 2 days we'll shift to multiplication of vectors and so on. So today our focus will be on adding vectors and a method that we call the end-to-end method. So when you are graphing vector G, which in component form is 2, 5, the first thing that you need to understand is that unless you're told differently, we start all vectors at the origin. Origin means starting point. So we're going to start at 0, 0, and we're going to end that vector at 2, 5. So there is vector G. So once again, unless you're told differently, vectors start at the origin, and it will end at the component form of 2, 5. Now what we're going to do is we're going to add to vector G, we're going to add vector H. Now here's where you have to pay attention. This is called the end-to-end method for a reason, and that's because the vectors are end-to-end. So we're going to start vector H at the end of vector G. They are end-to-end. But what we're going to do from the end of vector G is we're going to go in the x direction 6, and we're going to go in the y direction 4. So it's almost like you're taking the end of vector G and you're translating it. 6 to the right and 4 up. And when you do that, and you might, if you want to go in the y direction first, you can. It doesn't really matter. But the key is you're going 6 to the right and 4 up, and that would be the end of vector H. And once again, what we did from the end of vector G is we went 4 up, 6 right, or 6 right, 4 up, however you want to think about that. And so, if we add vector G plus vector H, I said there was a lot in common with matrices and vectors. When we add matrices, we add the corresponding elements. When we add vectors, we add the corresponding elements. So G plus H will end up coming from, or lead to, 2 plus 6, 5 plus 4, or 8, 9. Now, if you look at the end of vector H, where is it? It's at 8, 9. So we need to draw the resultant vector that will show that movement in one movement, and that will be from here to here. And that is vector G plus H. So when we're adding vectors via the end-to-end method, we need the first vector, which is there. And then from there, we're going to draw vector H, and then we always end it with drawing the resultant vector. And this vector right here is that resultant vector. And the first couple of problems that you're doing in the homework with end-to-end method, that's all I'm having you do is drawing the resultant vector, just to make a point. And that is, you have to end the picture with the resultant vector. Okay? And so that's how we do vector addition arithmetically. This is how we show or prove it graphically. All right. So I would like all of you to do number 7. Arithmetically and graphically. All right, let's take a look at number 7. Now remember, we need to graph vector A first. And remember, unless you're told differently, the first vector will always start at the origin. Now, first I'm going to do this arithmetically. So 3 plus negative 4 is negative 1. So the component form of vector A plus vector G is negative 1 comma negative 8. And then I'm going to show it graphically, once again starting at the origin. So I go to 3 comma negative 5, which takes vector A to there. And then from there, you're going to go negative 4 in the x direction, negative 3 in the y direction. So technically that means 4 to the left and then 3 down. And that will be the end of vector G. I went 4 to the left and 3 down. And then we have to end that by showing one movement, which is the resultant vector, which is vector A plus vector G. And notice that the resultant vector will always end at whatever you got arithmetically, negative 1 comma negative 8. And you can kind of think of the graph as a way of proving that it really is what you say that it is. Okay? All right, everybody do number 8. All right, let's take a look at number 8. First of all, arithmetically, 3 plus 4 is 7, 5 plus 3 is 8. So in component form, vector A plus vector G is 7, 8. Graphically, we start at the origin, go to 3, 5, and then from there, go 4 in the x direction, 3 in the y direction. So in other words, 4 to the right, 3 up. And that's where we should end. And then don't forget to draw your resultant vector, which looks like that. Now I'm just going to tell you a common mistake in my open math. So everybody needs to really be listening here, because some of you are going to think, I did it right, my picture looks right. But the most common mistake is to draw these vectors in the wrong direction. All right, you have to start with the first vector, and it's going from there to there. Notice that the arrow is there. And then from there, you need to draw the next vector, and then your resultant vector has to be going in the right direction. In other words, this direction in this picture. If you draw your resultant vector this way, even though the picture looks pretty much the same, it's going to be marked wrong. The vectors have to be going in the right direction. So make sure when you're doing the homework that you are actually doing that. Okay? All right, so that is the end of day 1, but one really quick thing here. Why do we bother graphing vectors? Well, the real reason is this. In physics and other math classes where you're doing some real-world problems, you might be asked this. You might be asked for the angle in between those two vectors, depending on what the situation is representing. And the only way to do that is by doing what we are doing. And so today we learned how to do this. We know today how to find the magnitude. In 2 days, we'll learn how to do this, which is called the dot product. And then in a later math course, you'll learn how to deal with inverse trig functions. But that's one reason why we have to learn how to graph vectors. And that's basically how you do it right there. By the way, the angle between those two vectors is 110.2 degrees. All right, end of day 1. You can go ahead and get started